Hello, Hafaday, and aloha. Thank you all for joining us today. Welcome to the first webinar in the Pacific Desk 2023 webinar series. I am David Hitzel, the Pacific Desk Guam instructor. Today's topic of discussion is space weather, forecasting and impacts. Our usual reminders before we begin: this is being recorded for educational and documentational purposes and is posted simultaneously on Facebook Live. Please leave questions in the comment section, including your location and affiliation. Questions can also be asked through Facebook Live, but a period of oral questioning will be allowed at the end of the talk. Please otherwise refrain from having your video or audio switched on at any other time. And lastly, the video recording will be saved to view later on Facebook and YouTube as well. Okay, so there is, as you might have heard, there's currently a very serious typhoon that is headed toward Guam. As I mentioned, I'm the Guam instructor, but I'm in Honolulu today. Otherwise, this webinar would probably be canceled. Typhoon Mawar is currently categorized as super typhoon with maximum winds of 135 knots, gusts to 165 knots. Unfortunately, all the model solutions over the last couple of days have suggested that it's going to be a direct hit. Also, the storm is moving slowly, so heavy rain is expected in addition to the high winds. So if you have friends or family on Guam, you might want to check in with them, or definitely check in with them over the next day, make sure that they're doing okay. All right. Our next webinar in mid-July will discuss the plan to install tsunami detectors on the global underwater cable system as a part of the Smart Cables Initiative. Our speaker will be Dr. Andrei Nadarov, who is an oceanographer with the Pacific Tsunami Warning Center. And then the following webinar in late August will provide an overview of wildfire across the Pacific and current efforts, programs, services, and international resources to informational resources to mitigate wildfire. Current opportunities in wildfire science, including participating in the PIA Wildfire Network, will also be discussed. So the speaker for that webinar will be Elizabeth Pickett, who is the co-executive director of the Hawaii Wildfire Management Organization. So those are in July and August. Okay, so today's speaker is Mr. Shawn Dahl. He is a U.S. Air Force retiree of 22 years, where he spent most of his career in the field of meteorology and space weather. He retired from active duty in 2007 and was hired as a lead weather forecaster at Scott Air Force Base in Illinois, where he was responsible for aviation hazards and meteorological forecasts for USAF missions around the globe. He moved to Hawaii to work for the National Weather Service from 2012 to 2015, where he handled the Upper Air Program, managed Kauai Island's Cooperative Weather Observer Network, and conducted education and outreach programs and initiatives. Finally, he was hired as a physical scientist by Space Weather Prediction Center, SWPC, in 2015 as a space weather forecaster, and he is now a senior space weather forecaster and also works impact-based decision support services, issues, and relations on behalf of SWPC. Okay, so the topic of space weather, I think is not familiar to your average meteorologist or forecaster. So I thought for my brief introduction, I would take everybody back to basics, back to high school physics, and talk about this curious word, electromagnetism. So in level 1 training, we introduced this strange word, and we introduce it in our discussions of satellite sensors, and that certain sensors see various portions of the electromagnetic spectrum. Visible light is one portion of this spectrum, as are microwaves and infrared. So early in the 19th century, various scientists began to piece together that there is a connection between electric charges, electric fields, and magnetism. These scientists were Carl Gauss, Michael Faraday, and Andre Marie Ampere. These three people provided a good conceptual model or law describing the relationship between electric fields and magnetism. But it was James Clerk Maxwell who took the totality of all their work and expressed these relationships mathematically. Importantly, Maxwell was also the first to determine that the speed of propagation of electromagnetic waves was the same as the speed of light, and that visible light was a form of electromagnetic waves. He also figured out that if current of electricity varies with time, it will not only produce a magnetic field, but an electric field as well. And then if this varies in time, it produces a propagating electric field, which induces a propagating magnetic field, which another way of describing an electromagnetic wave. So the first of these laws, or the first two actually, are Gauss's laws. So the first states that electric charge acts as a source or sink for electric fields, meaning that you get divergence of electric field from positive charge and convergence from a negative. The second one basically states that you can't end up with a north or a south magnet. If you break a magnet in half, you're going to develop new north and south poles, and you always have a closed loop for your magnetic field. 3 and 4, Faraday's law and Ampere's law, are the ones that are most important for the talk today. So that these laws suggest that you can create a magnetic field with a current, with electricity, and similarly, you can go the other direction, and with a magnetic field, you can produce an electric current. So that's Faraday's law and Ampere's law. So what does this have to do with? What does this have to do with space weather? Well, the Earth is a magnet and therefore is surrounded by a magnetic field. The sun also has a magnetic field, but more importantly, the sun is constantly ejecting a plasma of charged particles, like an electric field, the so-called solar wind, which travels along the sun's magnetic field lines as they radiate outward. When the solar wind reaches Earth's magnetic field, it is deflected by the magnetosphere, basically the outside of the magnetic field, causing most of the energetic particles to flow around and beyond us. This is a good thing. However, it is only a quasi-stable arrangement, and excess activity on the surface of the sun can lead to disruptions in the balance, which can in turn lead to disruptions in electromagnetic signals here on Earth, which means disrupting our communications. Such situations are what will be discussed here today as space weather. And with that, I will turn it over to Shawn.
All right, great. Let's see. All right, I'm thinking my slides can be seen now.
Yep.
All right, perfect. Well, hello, everyone. Aloha. It's nice to be back, even though virtually only, I guess, unfortunately, out the Pacific region. I mentioned I was on Kauai for a couple of years, working for the Weather Service out there at the data collection office in Lahui on beautiful Kauai. All right, so the Space Weather Prediction Center, that is where I work. I'm not there today, as you can probably tell by my background, all my little fleet of telescopes here behind me. I'm teleworking from home today. We don't get to do this very often, but in one of my capacities doing education and outreach, it's very helpful that I can do that. So if you could be here at the Space Weather Prediction Center in person, you'd be looking in through these two giant windows in here into the forecast office. And we have tours coming through all the time, especially now that COVID's done once again. These are showing back up. And we have a great mix there. Not only are we a forecast office doing 24 hours, 7 days a week operations and forecasting, but we also have a great science community here as well. So we're a group of not just physical and space scientists, but also administration folks, budget folks, information technology type people, a lot of people to make this operation center actually work. Those space scientists that we have here in particular, some of these are world-renowned experts in their field of a specific field of heliophysics. So if I have a question or a concern about a certain type of activity, it's really convenient and nice being in a national center that I can just pick up the phone or walk up to their office if they're here and ask a question, or have them come down and have them take a look at something. So, not everybody has that luxury. So it's great that we have that ability here at SWPC. So lots of government legislation and laws and bills have been enacted here quite recently, really over the last 5 years or so, as the federal government has become very concerned about the possibility of a space weather catastrophic event. And by that, I don't mean worldwide disaster, but in particular, something like the power grid dropping out. And if that was to happen, it wouldn't be just for a part of a town or a city or a county or even a state. This could encompass states in coverage, just looking at the continental United States, for example, especially in the northeast part of our country. And that is concerning to our government. So a lot of these things you see on this slide here are just many of the types of things that are still involved, even to this day. Just a few months ago, that bottom right picture was taken with the Space Weather Advisory Group and the NOAA administrator sitting there working out details for space weather, how to prevent a space weather event, what we can do to better forecast these events, and so on. So this is something that's always in the works. And why does our government care? Besides the reasons I just told you, well, a whole litany of things on this slide right here that you can read through. But the yellow banner on the bottom really pins it down. If we had a catastrophic collapse of a good chunk of our power grid in North America, we're talking about the potential for a $7 billion loss, because this is not something that would last for a few minutes or even perhaps just a few hours. This could last days. In the most extreme event, as unlikely as it is, we still is a possibility that it could happen. It's done it in the past at these levels of activity that could have that kind of impact to the grid. So that is the concern. What would happen today in our most extreme space weather storm that could cause this type of activity? We still don't know. It's all speculation, but the risk is there. And that's why the government is so invested budget-wise, money-wise, research-wise to operations to do a better job at predicting these events and helping figure out how to mitigate them if they were to happen or be a threat of happening. So what exactly is space weather? Lots of stuff's on David's slide that brought you back to your classrooms. I'm not going to go that route. I'm going to just tell you straight up what space weather is and what's going on. And I can make it as simple as this on this slide. What's happening on the sun in that vacuum of interplanetary space, that 93 million mile gap between the sun and the earth, and ultimately at here and around our planet, in particular with what's going on in our atmosphere or our magnetic field, as David alluded to. So let's go behind those windows and into the forecast office. Here's where I work when I'm doing operations in there, whether it's day or night. And you can see the wide range of monitors in here. We need all these because we don't have a lot of incoming separate pieces of data. Like, for example, in the upper air network, there's hundreds of stations around the world. Well, we don't have hundreds of stations giving us data. We have only a few. So we bleed them for every ounce of information we can get out of them, whether it's a satellite in space or a magnetometer observatory over in, say, Fredericksburg here in our country or Europe, whatever the case may be. We try to filter as much of that into the office so that we can just scan around the room from monitor to monitor and pay attention to what's happening and make decisions as we go about our business, creating forecasts or putting out watches, warnings, and alerts. And now perhaps advisories for the aviation community when we're that center. And I'll talk about that here later as well. So we have a lot of core partnerships to make this happen. We have a very strong working relationship with my old comrades in the Air Force. Not only do they have their own space weather center that we coordinate with every day in Offutt, Nebraska, but they just routinely, we have to interact with them because they provide a lot of the information to us, especially on the ground-based observatory network that the Air Force manages, both radio and optical. Now we're talking work with FEMA, and we're talking work with the NERC. If you don't know what the NERC is, that's the North American Energy Reliability Corporation. They're one of our biggest core customers, if you will. We alert them for certain types of activity, and that's basically the entire power grid of North America. So you can see that that starts to get important. Some of our more of our core partners that we work with that are outside of what I showed you there. We got the UK Met Office in England. So we work very closely, and our National Weather Service director just made an arrangement with the Met Office about a stronger collaborative working relationship with the UK Met Office right there in the UK. So that'll be interesting to see how that evolves and how it works. But right now we have a very great working relationship. So it's not going to be hard to make this happen. It kind of already is. It's just making it official. We work with NASA. We're starting to work more and share information with Canada. USGS provides us a lot of the magnetometer data and more. So like I said, this site could be bullet ridden with all sorts of stuff, but we don't have that. We have some agencies and entities that are able to give us information to do this function. As far as how we get what we get, as an example here, we're really focused on observatories, whether it's optically like ground-based telescopes or ones that are on satellites in space. There is instrumentation on the GO satellites, the recent ones that have all the regular terrestrial weather packages taking pictures of clouds on Earth. They also have telescopes on them that are taking pictures of the sun at various wavelengths and temperatures of light to allow us to see what's happening. You saw some of that imagery on that earlier picture on the background wall. Telescopes that the Air Force manages. I worked at one of these on the top right on the island of Puerto Rico for 4 years in one of my assignments. Monitored the sun day in and day out and reported on sunspots and other activity going on right to here, as well as the Air Force at the Space Weather Prediction Center. So some of these satellites have gone on orbit around the sun and are on their way back. Right now, they're almost back to a direct line between the sun and the Earth, well, about 1 million miles from our planet. We have other satellites at that location as well, because it's a perfect spot to maintain an orbit equally between the sun and the Earth, between those gravitational poles. And that allows us to see what's coming towards the Earth from the sun. Mind you, it's only 1 million miles, not 93 million miles away. So in the most extreme events that are traveling through the solar wind, we may not have a lot of lead time here, but we do get lead time. At the very worst, maybe about 15 minutes, but in most cases, we can have a little bit more time than that. So what is it about the sun that makes it interesting at times and dull at other times? Well, it's the solar cycle, just the way the sun operates. It's like Old Faithful in Yellowstone Park, if you had the privilege of being there and visiting. The sun works on a cycle. It has to do with its magnetic field. And that allows the sun to have periods of maximum activity, peaks of sunspots and other measurements we take in the sun where activity can be abundant, and then very quiet periods where we may go for months without seeing a single sunspot on the sun. So that's that valley between the peaks you see on that chart, and the tops are those solar maximums. This only goes through solar cycle 23. We are now in solar cycle 25, and we are working our way quickly up the peak, which is expected to be in about 2 years from now. And why does this happen? Why do we have a solar cycle? It's because the sun rotates. But it doesn't rotate equally. The equator of the sun is actually rotating much faster than the poles of the sun, 10 days faster. And that it doesn't mess with the sun itself because it's a plasma that kind of works like, liquid dynamics and such. But what it does mess with is its magnetic field, because it allows that to twist up because the equator is rotating so much faster, it pulls that magnetic field. And over time, month after month, over this 27-day average rotation, starts to wrap around itself. And it becomes very chaotic and mixed up, the sun's magnetic field. And this is when we have activity really begin to bloom on the sun. Sunspots, for instance, like you see here in this roughly 30-day composite animation from the Solar Dynamics Observatory operated by NASA. You can see these sunspots. You can see the sun is clearly rotating. You can see sunspots emerging in front of our eyes, some rotated into view, others that are taking themselves out of view. And I don't know, I hope I'm still coming through. I see my video went crazy there. Let's run that again. You can see some of these sunspots are pretty dramatic and intense at times. And this is where we focus and look for potential for sunspots and possible activity that could be taking place. What do we do about them when we see them? Well, we have to analyze them and look at them very closely because they are normally the source of most solar storms. Not all of them by any stretch, but most. And I'm going to take myself off video since that keeps getting hung up. When we see these and we know they're lasting long enough and they're going to be there for some time and they've been corroborated by several observatories, then we'll give them a number. It's usually a sequential number. So in this case, on this example, the next one would be 3406 if we chose to number one. Right now we're at 33 something. So you can see we've got a complete rotation here through the whole sequence as for our sunspot sequencing numbers right now. Now, when we look at these, we're looking at their magnetic field. You saw this, hopefully this was running. Let's try this again. Back up the slide, move forward, see if this animation runs. And you can see the magnetic field appear before your eyes. The black and white imagery represents the negative and positive polarities here. And you can see how those overridden right where the sunspots are. That's because of these strong, massive sunspot groups appear on the sun. It's really embedded magnet localized areas of magnetic flux which pop through the surface of the sun. And if they're strong enough, they reveal themselves as these sunspots. It kind of blocks, just think of it as a reverse plug. It's a magnetic field that's strong enough that blocks the normal flow of convective flow, if you will, of energy coming from inside the sun. So these areas are actually much cooler than the surrounding surface of the sun, the sunspot groups themselves. And this is where we're really focused for flare potential from these events. And how do we do that? Well, it's the same way that we do any kind of forecasting in the Weather Service or in the Air Force or whatever field of meteorology you work in. Same thing, we go through the same types of steps we always do with meteorological forecasting. It's just that we think about things quite a bit differently than regular terrestrial meteorology. Even one of our analysis products that we put out twice a day called the Solar Synoptic Drawing that you see on the upper right is looking at different things. Instead of fronts, we're looking at neutral lines of magnetic fields, that area between positive and negative polarities. We're looking for other features called coronal holes, something I won't talk about today, but is something that is important to geomagnetic storm forecasting. Sunspot groups and any other features of note like prominences and filaments. And we'll talk about some of these as we progress today. So what is it that we're doing with this information? Well, we do forecast various things, but the big three are these right here. And it's really impact-based forecasting. We're looking at the events and what is actually creating those events. So we are, even though we're forecasting the chances and probabilities of a solar flare to happen, or a solar proton, energetic proton event, or coronal mass ejection in some cases, we're really looking and focusing on the impacts from those. So solar radiation storms, that equates to our S scale on our NOAA space weather scale. Radio blackouts refers to high frequency HF radio. And you're going to find out today how important that is and could be for Pacific operations in particular. Geomagnetic storms, something that maybe isn't too much of a factor out in the massive Pacific and in many locations, especially those more equatorward. But it is a big deal here in the US and perhaps Alaska and other more northern or southern line locations. Solar flare radio blackouts. So here's why this is important, because when we have a solar flare happen on the sun, the effect is almost instantaneous. Well, it is instantaneous. We see the flare and the impact is already going on in our outer atmosphere on the daylit side of Earth. And when it gets to strong enough categories and levels, it could cause a complete blockage of any ability to transmit via HF radio because the atmosphere absorbs it. It's become too ionized and energized, and radio signals can no longer refract or bounce off of them. In 2017, this was a really good example of terrestrial weather event. We just heard about the terrible typhoon that's going to run across Guam. Well, in 2017, and we had Hurricane Irma, among others, that were ravaging the Caribbean Sea. And on the island of Puerto Rico got damaged by one of these, if not that one. I don't remember which one hit it, but it was a terrible year in the Caribbean for hurricanes. Well, we happen to have one of the strongest solar flare that we had the previous solar cycle happen at the same time this was going on. And this caused an enormous radio blackout across that section of the world. And unfortunately, that was the way they were trying to communicate, because telephone lines were torn apart. Electricity was out because of the terrestrial weather problem with the hurricane. Cell phones were inoperable because of the towers were pulverized as well. And people were reaching into their ham radio, their HF radio bag to communicate. Air traffic control was having problems during this event because they couldn't communicate with their aircraft that they were responsible for in certain cases. Very disruptive event. It was long lasting as well. Most of these flares are impulsive, meaning they're very quick. They may just be a few minutes in time. The stronger ones, sometimes they can be longer duration and go on for many minutes and even a few hours at intensities that could cause this kind of disruption that you see here on this slide. Think about the Pacific, your typhoon watch networks, your hurricane watch networks. A lot of these use a ham radio. This is what we did in Kauai. Some ham radio operators would work out of our office there in an emergency. Well, if you have a solar flare strong enough that happens to be on the daylit side of the planet where you're trying to operate one of these systems, it can be impossible at times in the worst case scenarios of these events. So yeah, very disruptive these solar flares can be, especially for your concerns out in the Pacific. These happen just a few days ago, May 20th. A solar flare happened. It only hit R2 levels. So that moderate level wasn't strong, wasn't severe, wasn't extreme, and yet it was disruptive to air traffic control in the Atlantic Ocean, and particularly around the Caribbean HF groups, as you read that message posted by New York Air Traffic Control Center in New York State, courtesy from one of the folks there. So yeah, very disruptive event. The map I show on the right, courtesy of Wikimedia, is something I pulled to show you where the daylit side of the Earth was when we had that flare happen, and that yellow circle represents kind of the subsolar, meaning where the sun was directly overhead. So yeah, even at that moderate level, barely moderate level, it was really almost an R1 event, was very disruptive. So imagine the higher ends of our space weather scale and what that can do at just the right times when air traffic control needs to communicate. So what do these events look like? Well, they look like this. This is the 2017 flare that was so disruptive, especially post-hurricane stuff in the Caribbean Sea. And so when we have these events, like I said, it's the sunlit side of our planet that's impacted, and the stronger these flares are, the more widespread they're going to be in their coverage. Scary looking map here, scale, don't worry about it. This is just the way to show you what you're looking at if you ever go to our page and you want to see what kind of solar flares are happening, or if it's still going on, what level it might be, things that you're not going to get up-to-date information from us. But you can look at this data real time on our webpage. It's coming right from the GOES satellite and processed and put out there. So the normal scale here, just if you look at the right side, you see these letters of A, B, C, M, and X. Well, A and B's are kind of normal background levels. When we get around solar max, we kind of climb into the C levels, at least the low C levels, for kind of a background flux, X-ray flux of the sun. But when we start getting into those M levels, now we're in our space weather scale. So M1, M5 type flares are in that R1 to R2 category. We get X1, we're at R3, X4, we're at X10, we're at R4, and X20 and above, we're at R5 type events. So that's kind of how the scale works, and you can get an idea for yourself on what's happening. These are what we're forecasting the probability of, is what level of flaring and what the probability is that we're going to have, and what's the percentage chances that these may happen. And you can read about those in our 3-day forecast and forecast discussions. What else does the sun do that's impacting? Well, it sends out radio signals. Sometimes when you have a solar flare, or even without one, you can get a tremendous radio storm on certain frequencies. Some of these frequencies happen to be the same one that air traffic control operates on. As you see in this example, this happened in Sweden some years ago, where the radar happened to be scanning and right facing at the sun on its scan, and it was just the right wavelength where it made it look like jamming and they couldn't see their aircraft. Pretty scary if this were to happen at a busy airport such as Honolulu or major metropolis like New York City or Los Angeles, right? So this is we don't try to forecast the events. It's science just makes it impossible at this point. And so our warning ability on this right now is even limited as well, but it is something we monitor. Solar radiation storms, not too much of a concern for the Pacific region, except if you're in and around the polar regions and you have flights that go through those areas and you manage them or deal with them. This is where they can be impactful. Right now, due to the Ukraine war, we're not flying. There aren't flights flying over close to the polar regions anymore. So when we go back to that, which eventually we will, because it saves tremendous amounts of fuel and time, then this will become problematic once again. But not only can this cause a hazard for an inability to communicate via HF radio over these polar cap regions when we get strong enough activity from these types of storms, and these usually last days, many hours to days. They can also cause radiation exposure to the human body at high altitudes, at those higher latitudes, more northward or southward Polish. Just kind of an idea of some of the things we're looking at. Because we do aviation support, we're looking at various models to help us determine what those dosages may be. to warrant such an advisory that I'll talk about here towards the very end. Rocket launches, big deal now. New Zealand's doing rocket launches right now. We've had calls from New Zealand with some of the latest launches where they've actually postponed the launch due to some of our space weather forecasts that we're looking at, due to either radiation storm potential or geomagnetic storm that could influence their ability to navigate their GNSS systems that they were relying on in some cases. So yeah, a very big growing industry. It's not just NASA doing this anymore from Cape Canaveral. These are done at various places in the world, and we are getting more involved with this type of support as well, because these rockets will not launch, depending on what their capabilities are, during certain types of these solar radiation storms, which are caused by energetic protons. It depends on what the energy level is and the number of them, but they may scrub their launch when we get to even lower levels on our scale with this type of activity, because they don't want to take the chances of one of these solar energetic protons penetrating into their equipment at just the right time, just the right angle, that causes some kind of upset in the electronics just for a split second, which could take the rocket off course and cause a catastrophic failure. What do these look like on some of our satellites? Well, like you just see in this animation on the left here, that's a solar energetic proton event, a solar radiation storm hitting one of our spacecraft that we monitor and look at the sun's corona with to determine about certain types of explosions coming from the sun. These can be harmful to the human body at certain higher energy levels. So we've got astronauts going back to the moon. Artemis mission was just done with some mannequins here. Next one's going to have 4 astronauts on it in about 2 years or so. That's right around solar maximum. This is going to be a problem. We'll be having to forecast these events as we always do, but also predict duration and maybe when the end time is, because they may have to take some extreme measures for their protection, because they're going to be outside of the realm of our protective magnetosphere and, of course, our atmosphere. Similar chart. There's a platform on the GOES satellite as well. Here, this is reaching all the way back to GOES 11 with this example. We're at least at GOES 18 now, but same type of equipment's on there, just improved and better. And same thing, our scale goes 1 through 5. This is the S scale, and we're looking only at the 10 mega electron volts protons here. There are higher energy levels, 50, 100, 500, that are concerning to different agencies or needs. But for our purposes, our warning that we deal with our forecasting is just at the 10 MeV level. We put out one warning when we're expected to reach that level of S1. We don't do it beyond that, but we do issue alerts at every level and then update the warnings accordingly as needed. When we get to those 500 million mega electron volts protons, that's concerning. That's when we can have radiation exposure at the high altitudes. And this is where it would become a problem for aviation. Prominences and filaments are things that we're monitoring for on the sun. Strong magnetic fields not only create sunspots, but they can trap solar plasma and keep it entrained out there. And as that magnetic field becomes unstable, as is always happening in the sun, that's why we have solar flares, that plasma will begin to move around, as you can see in this animation. And we'll start to see solar prominences expand or move around. Perhaps gravity pulls it back down to the sun, as you see in this example, and nothing extraordinary happens. Just kind of a quiescent, active prominence, maybe a small eruption there, but nothing we could really note of any significance. But sometimes they're much more dramatic, and it's obvious something important happened, as you can see here, where it's like somebody just flung a rubber band, stretched it off into space, across a room. So this, you can even see the solar flare that happened along with that. So that is a solar filament that decided to lift off the sun because the magnetic field supported it, held it in place, became unstable, and it had to reconnect. And when it did that, it released energy not only back to the surface of the sun, but out into space in the form of that, well, billions of tons of plasma in just that animation alone. And that event went off into space. Now, these carry a strong magnetic field along with them. That localized strong magnetic field that was holding it in place has also now lifted off into space. And that's where that magnetism that David was talking about becomes important, because now you have not only billions of tons of solar material, you have a very strong localized magnetic field moving off into space in what we call a coronal mass ejection. This is an example of looking at that coronagraph we have in space a million miles from us. You saw the image earlier with the blizzard-like appearance. That was a different distance, same location, but looking at the sun with a larger area. Here's more close up, but it's the same satellite. That white circle represents the diameter of the sun. The black is the disk that blocks the brightness of the sun so we can see the corona like you could during an eclipse, kind of. And you can see how that coronal mass ejection, like that filament eruption you just saw, may look as it exits the sun. They expand rapidly. You can see the material lifting off, but unfortunately, we can't see the magnetic field that's moving out there as well. Now, we'll measure every single one of these events when we see them show up in the coronagraph here at the forecast office, because we have to see, could that reach Earth? Because just because it's lifting off to the side of the sun, or appears to be so, part of that may be Earth directed, because at 93 million miles is a lot of expansion time, and you saw how rapidly that can expand. So even those ones we take and look at, because it is possible we could see a very close proximity that could influence Earth, or even what we call a glancing blow. Sometimes it's a bit more obvious though when we get these things called full halo coronal mass ejections, as you see here. The most extraordinary of these events can get here in 15 hours or so, but usually they take about 2 to 4 days. We'll do the same thing here. This full halo CME, we'll analyze and parameterize and try to get an idea. We'll inject it to one of our physics-based models and try to determine when it may hit Earth, and if so, how strong may it be, which is really more of a guess at this point, but we do have some indications of that model that help us with that decision making. Why is this important, these events? Because these are what causes geomagnetic storms that not only can cause, well, look at them, read them on the bottom. You can see the many different types of things that geomagnetic storms can impact. Of course, the one that's most problematic and concerning for our government is a potential for the risk of a catastrophic failure of our power grid across our country or North America or somewhere else in the world. Could have these happen as well, and they have in the past, such as I believe South Africa had an experience like this. I think Sweden may have, I can't remember. I know Canada has in 1989. 2/3 of the province of Quebec, Canada dropped out because of a geomagnetic storm that reached such levels that it caused direct current to show up on an alternating current system, which is always a bad thing. That induces massive amounts of voltage across their transmission lines and causes problems at transformers. What happens when a geomagnetic storm, when a CME arrives at Earth? Well, once again, thinking about David's magnetism slide. So Earth's magnetic field comes out the bottom of our planet and goes into the top. So just think, if you turn your thumb downwards, coming out the bottom, and then turn it up, your thumbs up, going northward. So it's pointing up as it goes back into the North Pole. So when we have a coronal mass ejection arrive here at Earth, I'm starting my video, and hopefully this holds this time. So you have the strong magnetic field expanding off into space. Well, that orientation of that magnetic field makes a huge difference at what happens here at Earth, because our magnetic field coming out the bottom, going into the top, thumbs up. So if that CME arrives here at Earth and is the same orientation or stays the same orientation as it arrives as Earth, it's going to be like putting two negative magnets together or two positive magnets. They won't connect. It'll be a sudden hit. We'll have some reaction happen immediately because of the induced current around our planet and onto those systems, but we won't connect. So it may not reach the levels that we're looking for or are possible that would be with the strength of that event. However, as it's passing through, if it turns southward and stays southward for some times or arrives southward, boom, it's like putting a positive and negative magnet together. They connect. Now you get activity, not only connected in the front of our planet, but in particular in the magnetotails surrounding behind our planet. And that is where we get these strong storms spin up. So that's sometimes why we may be forecasting a stronger event, say a G3, but we get a G1 or we get less than a G1. It happens because we never know what the orientation is going to be. We have no science to help us decide that. No ability to do that. We have to just look at the potential without that knowledge, which is very difficult. We won't know what that is until it reaches the satellite 1 million miles from Earth. That is when we hit what we call the A satellite or Discover satellite, which is measuring the solar wind field, and then we can see the orientation of that field. So if you look at that top plot here, a lot of you might be weather folks, so this may be of interest. That's the magnetic field. That white line represents the strength. The red line represents the direction. So when it's negative, it's southward. When it's positive, it's northward. So that'll give you an idea of what's going on, and you can see how these CMEs can rotate with that magnetic field. The yellow line represents the speed. So in this particular CME, this arrived with some force. We were already in what's called the coronal hole, a high-speed stream. We had pretty elevated speeds, over 500 kilometers per second. And then boom, we quickly, rapidly went up to over 800 and then approached 1,000 kilometers per second. That's enormous. That was a very strong CME at this point in time. The model that we have to use these is called the WSA-Enlow model. Very subjective. It takes a lot of different analysis and forecaster looks at these and each result that we get to determine which one we want to go with before we pull the trigger and make a decision on what we want to forecast and put out any applicable watches for that event. When they're strong and they arrive, I mentioned regardless of what the magnetic field is, arrives with some force in the stronger events. So much so sometimes that they can crush our magnetic field inwards, where the GOES satellite, which is normally residing well inside of our magnetic field, can suddenly find itself on the outside when it's, between the sun and the earth on that side. That's when we know we had something called a magnetopause crossing, and that can cause some problems with certain types of satellites that rely on the magnetic field for their orientation. What are we looking for? Here's a very complicated slide. I don't have a lot of time to talk about this with you, but just know there's two scales. There's the KP index, and then of course our NOAA space weather scale, the G scale, the 1 through 5 scale. Well, there's also the KP, the kind of 0 through 9. Just know that anything 0 through 2 is quiet. 3 on the KP is unsettled. 4 is active. 5 gets to G1, 6 to G2. We do this type of correlation all the way till we get to K of 8. K of 8 through K9 plus. And believe it or not, each of these categories is divided into 3, a minus, a 0, and a plus. So K9 plus is, K9M is still a G4 event. K9Z, we can't really measure beyond that. That's now a G5. So in this case here, we're hitting G4 levels at KP of 8. It would take a KP9Z to be a G5 event. We've had a few of these already in the last couple of months. So even though we're only 2 years from solar maximum, or predicted solar maximum, we're already having some pretty notable activity here. Just kind of a review, we put out watches, warnings, alerts as well. Watches for us can be 1 to 3 days in advance, unlike a normal weather service watch. Warnings are the same kind of thing when events are imminent. We don't put these out when something's been proven to happen. No, that's what the alert's for. So once we detect these as happening, we put out the alert. Some of the products that are out there that are on our webpage, you can explore these for yourselves, but the one of most interest to you would probably be the 3-day forecast and the forecast discussion. Each of these are put out twice a day. They're issued at 0030 UTC and 1230 UTC. The 0030 UTC is usually the driving one. That's the one the day shift forecaster puts together. And then overnight shift does the second one, which is usually just kind of an update. Some of our IDSS support, this is growing. And we're becoming more involved with other things. I won't spend a lot of time here, but just to give you an idea how this mission continues to grow. Not only its responsibility, but requests for information. I mentioned we're doing aviation support through the International Civil Aviation Organization, ICAO. So right now it's every 8 weeks. We do a 2-week stint here at SWPC where we are the Space Weather Center for ICAO. So we're putting out advisories for the 3 things you see listed here, and these break down into other categories. But this is our responsibility for 2 weeks at a time. Russia-China consortium just came on, so they are the 4th consortium. That's why it's every 8 weeks now. South Africa Regional Center, it's my understanding that they're going to want to be another one or be part of another one. So we may have eventually 5 of these centers here at some point, which would put us every 10 weeks doing this. But yeah, things are getting more active. It's getting more difficult to maintain this responsibility as well. Here's where we're at in the solar cycle. The red line represents the median prediction. You can see that solar max was predicted to be around 2025 to 2026 timeframe. That gray shade represents kind of the margin of error. We're above that margin of error for the most part already. So what does that mean? We don't know. Don't know if that's going to mean a stronger solar cycle or a quicker. Remember, that's 11-year average. It means it can be 9 years, 10 years, or go on for 12 or 13. So we still don't know what that means. We just know that it is definitely outside the margin of error at this point for the most part. Types of notable space weather events. This isn't all of them. There's been others. Just to give you an idea of some of the types of things that have been massive. Look at the most recent one that's listed on this slide down at the bottom. SpaceX lost 38 out of 49 satellites. You may have heard about that. And that wasn't even from a moderate or higher geomagnetic storm. That was mostly active levels at KP of 4 to G1 levels. That did things to our atmosphere and neutral density that caused these low Earth orbiting satellites to plummet back to Earth very quickly. It was like within a day or two or something like that. So that was a massive loss for SpaceX and Starlink. So they're starting to catch on that this is important, that there's other things that factor into their decision making and engineering for these types of things. Even more recently, just a few months ago, we had a massive coronal mass ejection. It was a full halo, but it was not aimed towards Earth. It was on the other side of the sun and went the other direction. That one actually produced a solar radiation storm. I didn't talk about it, but when we get proton events from the sun, it's really about the location of, say, the sunspot complex that caused it, or was the source of it. They have to be further to the side of the sun on what we call the west side of the sun, which would be the right side of the sun as you look at it on imagery. That's where the magnetic field that curves out into space connects with Earth. And these particles spiral along those magnetic field lines. So that's how they can reach Earth. So the fact that we had a minor solar radiation storm from an event that happened on the far side of the sun is incredible. Tells us there was a lot of power to that event because that crossed magnetic field lines, a lot of them, which isn't easy to do physically. So that told us that if that had been aimed towards Earth, that may have very well been a pretty strong event. We certainly would have had a heck of a solar radiation storm out of that. We're getting more involved with emergency management across the country. They're putting stuff into their hazard identification and risk assessments, especially here in the northeast part of our country and the northern tier states, and even some of the central plain states here are now getting interested in space weather. So how to stay informed? Well, you go to our webpage. You can find everything right on there. If you haven't explored it before, I encourage you to do so, even if it's just kind of a hobbyish bit for you to learn more about or stay aware of. How do you get informed? Well, you subscribe. You subscribe to our product subscription service or the National Weather Service INWS system, and then you can get these right to your phone as text messages or into your email, depending on how you choose to do it. What does the public want to know? You know, most space weather events aren't going to do anything to the public. We're always safe from these storms to our atmosphere and our magnetic field, as long as we're here on the surface of our planet. But, you know, especially here in the CONUS, in the continental US, people are interested in the aurora when they get a chance to see them. And these type of events start to get public attention, media, press attention. What does this mean out in the vast Pacific? Well, if you start to see the aurora in Hawaii, there's a mighty storm going on. You know, if you see it in Samoa, or some of these locations you just never would likely to see it. That means we have an extraordinary extreme event going on our hands. It's possible. It's happened in the past. So something to be aware of as we move into this next solar cycle. And what would that mean for people that don't know about space weather, that have never seen the sky lit up? You know, things to think about. So that's all I have for you. If you have questions in the future or want to reach out for additional information or talks or whatever, here's some emails and contact info for you. Mine on the bottom there. As I mentioned, I'm a forecaster here. So I work rotating shift work. My boss is Rob Steenberg. And one of our other folks involved in this stuff is Bill Murtaugh. He's kind of our program coordinator. But feel free to reach out to me and I'll point you in the right direction if I can deal with that. Mahalo, it's been my privilege to talk to you today, and I'm happy to take questions as we have time.
All right. Thank you, Shawn. Does anybody have any questions? You can ask questions. You can either unmute yourself or you can ask in the chat. You mentioned the Carrington event. I think if people want a fun way to learn a little bit more about this, and I think the Carrington event also, that was a case where you could see the aurora at very low latitudes.
Yeah, you could. It was 1859 was that event. And remember, we didn't have anything really studying the sun yet, right? Except an astronomer named Richard Carrington, who was actually making a sunspot drawing of a giant region of the sun. And he noticed these two white lights in the sunspot group show up. It's called the white light flare. It's a very rare event. So he actually made a note of it on his drawing. You can find it on the internet, that actual drawing. And then about 18 hours later, all heck broke loose here across the world. The aurora was seen at very low latitudes, even some very more closer to the equator. Let me shut that up here. And so, yeah, the aurora was seen at those levels, and telegraph operators were in business, and we didn't have telephone lines yet. And extraordinary things were happening. Batteries, stations were starting on fire, sparking. There's even a documented conversation where two telegraph operators disconnected their equipment, but there was still a signal. They were still able to send signals back and forth just to the electromagnetic energy that was built up on those telegraph lines, sustained, a level of electricity needed DC wise to operate their system. It's really quite incredible.
Okay, we have one question. How many extreme events are you seeing per year?
Yeah, probably, statistically in our stats, I think it shows something like less than 10, but that's kind of divided up into 3-hour periods. Normally, it's not even necessarily that much. To reach that level, especially the way it's defined now, would really probably be more on the possibility of, several times in a solar cycle. It doesn't mean it'll always happen, but at this rate of things that we've got going in this cycle, we don't know. We could potentially have a G5 event, or we may not this year. And if we do, if it's only short duration and we just barely reach it for, 1 3-hour period, and we measure these, it's like doing a rain gauge measurement every 3 or 6 hours. We take a sample, an estimated KP official read every 3 hours, and it kind of resets itself. So we reach G3, we may reach it again the next one, or we may not. So G5 may be one little quick period, and that may not have a major impact, but if it lasts for several of these 3-hour periods, now we're getting into a possibility where it could be an impact.
Okay, yeah, Craig, if you want to go ahead and use your microphone, you can ask a question.
Thank you, David. Craig Roger from the University of Otago in New Zealand. Thank you for the talk, Shawn. That was really interesting. In New Zealand, we have had damage to equipment in the power grid during the November 2001 storm, and the electricity industry in New Zealand is really interested in extreme events are potentially impacting us. The slight issue we have is that a G5 extends from being something that's extreme but probably not dangerous to us, all the way to something that is extreme to something that will be dangerous to us. So is there any plans to extend the scale from G5 to have maybe a G6 and a G7 that is not once a solar cycle, but once every 50 years or once every 100 years, that's actually going to be the stuff that we're scared about?
Yeah, thanks for that question. I know there's work underway to re-look at and redo the space weather scale, whether that's adding another category like ionospheric storms, or re-examining the best way to convey this information. And we're working with social scientists now as well to help make the scale more usable to people and industries in need at the same time. I don't know at this point if we're talking about doing anything above a 5 level on a scale. They've tried to keep it like the hurricane scale, only a 1 through 5 type category. That's kind of the way it came up that way. I can say this though, like geoelectric field models that we have here at SWPC now that were developed by Dr. Balch, along with some university work and USGS and such, is getting to the point where here, at least in North America, in the CONUS and now at some part in Canada, we can look at the amount of estimated voltage building up on a transmission line, per kilometer, and make it more local. So, we could have a G4 storm that's producing a lot more induced current on a certain section of our country, where a G5, because of the timing and where we're at in the 24-hour period, may not be doing so much. But that model gives us the ability to do that. So that's kind of the progress we're making, at least in North America. I can't speak for New Zealand and Australia and the Southern Hemisphere and what's going on, but that's the type of work that's probably needed to get a better idea of what might be happening for induced current on power grids.
Thank you, Shawn. We actually have those sort of models, but what we'd really like to do is getting the predictions from people like SWPC, so that once we've got a model scenario, we know whether to enact our mitigation processes in the country. Also, thank you very much for the call out about the launches into space from New Zealand. Good on you, mate.
Yeah, of course, you're welcome.
Okay, do you have time for 2 more questions, Shawn?
Yes.
Okay, one person, I came across this when I was reading about this, that there's ideas about having an early warning system, something like a Lagrangian point, somewhere that's a good orbit. We could put a satellite that could give us some heads up. What's the work on that?
Yeah, there's a lot of talk about these points, and these are specific orbital points that exist that allow the spacecraft to sit there without burning fuel all the time and maintain a position. So I talked about the satellite that's 1 million miles from Earth, that's what's called the L1 point, the Lagrange 1 point. So that's directly between the sun and the Earth, and that's about 1 million miles from us. L5 is another one that we're looking at, that some spacecraft are potentially, maybe even from Europe, I believe some of ESA is involved in that. Putting a spacecraft there, which would be downstream from Earth's orbit, meaning we'd see, if it was looking at the sun, we'd see what's going to rotate into view. Okay, it's not away from the sun, upstream of Earth. That would be a great place to have a spacecraft, because then we could parameterize better these coronal mass ejections to get a better idea of their trajectory. Kind of like, getting a 3D look at it. We had that with stereo for a while, that went around the sun, but now, that's going around the sun. So it's back, it's less than a day behind Earth now. So it's really not between that line anymore. But that's where we are looking at putting some spacecraft as well, along with additional ones at the L1 point. Those are the two most important ones. L2, there's some talk to get a better look back there, but that's really not serving our purposes. That's more for the moon. So there's a lot of interest in that as well.
Okay. Okay, sorry, there were actually two more questions after that. I don't think I should skip them. They seem important. One is, so if the satellite sees something that's going to be of danger or serious disruption, what can we do ahead of time?
Yeah, if the satellite operators that control those systems, usually they don't do anything. If they need to do something, they may put it, I think it's called a safe hold. I think that's a general term for most satellite operations, to help mitigate any effects. The problem with the satellite industry is they're not very revealing about impacts because of insurance reasons and such. So we don't get to hear a lot about what they're doing and measures. We are going to have the satellite community show up here this summer or late summer in a testbed experiment. We just did this with the aviation community. It was very successful. We're going to do the same with the satellite community. So maybe next time I'm asked this question after this testbed, we can actually provide a better answer of what they do, what they can do, and what impacts they, may care to share a little bit of that we don't normally get to hear about. So we're looking forward to that this summer to integrate with that community a little better. But right now, I don't have an answer for you about what they do and what risk they're willing to accept before they would, do anything more drastic for the satellite protection.
I think the question was more at like, what would we do here on Earth if we got an early warning? What can you?
Oh, right. Yeah. So, normally for the public safety, the public in general, nothing's going to impact them. None of these events I talked about is going to be impact to anybody on the planet physically. It's really about if you have an event going on, like say a geomagnetic storm, the potential for the power to go out at somebody's house due to a geomagnetic storm is very, very low, right? It's highly unlikely. So when we put this messaging out there, we're really focused on the public need not take any action. At least so far. Now, when we get to a G5 one, we'll have to re-examine what the intensity is, how long it's lasting. Maybe we, change that messaging a little bit. But right now, what we struggle with at SWPC is not to panic the public. They hear about this stuff in the press and they may get concerned and think they need to do certain things at their house. When if they're taking the normal precautions that they normally do for, say, a power outage because of a storm, because of a typhoon, a hurricane, they're good to go, because that would be the main concern for them. So there's no warning system in place to put out an alert that would go across the whole country, at least at this point in time.
Okay. All right. And the last question was whether other planets have an impact on Earth in terms of space weather.
No, not at all. Not really. There are gamma rays that are constantly flinging through space. So interesting enough, when we're at solar minimum, like the least amount of solar activity, our heliosphere around the sun is more exposed to gamma rays coming in from other stars, other galaxies throughout the universe. And that actually can cause some problems with certain types of equipment out there as well. It's just, not often, but it does happen. Where was I going with that? So solar minimum is when we're at more risk for that. What was your question again? Can you repeat it? I lost track of myself.
Whether the other planets have an effect.
Oh, yes. Thank you. Yeah, their planets themselves, no. But NASA does look at the other planets as far as coronal mass ejections go. We here at SWPC, we're only concerned with that sun, Earth, and moon line. you know, they got space, they got probes on Mars. They've got probes looking at Jupiter. They look at these events very detailed as well to see if that could have an impact on those research satellites that are out there throughout the solar system.
Okay, interesting. I guess it depends on how the planet's made up, what kind of magnetic field it would have, and how much protection. I guess that would be interesting to look how it affects other planets, the sun ejections.
Yeah, you know, as far as the moon goes, right here locally, from what I know. So when we have astronauts walking on the surface again, our first woman walking on the surface of the moon in 3 to 4 years, right? If we have some of these solar radiation storms going on, it's going to be very critical for the astronauts to be able to get back into that capsule on the moon and be as safe as they can and less exposed to, you know, it's happened before. We could have an S4, S5 event, meaning tens of thousands or hundreds of thousands of energetic protons are blasting onto the moon with no atmosphere, right? Here on Earth, we'd be totally protected still, not necessarily at certain orbits, but here on Earth we are, not on the moon though. So that'll be fascinating when we're back there on what may unfold.
Okay, great. With that, I will wrap up this webinar. Thank you very much, Shawn. A lot of appreciative people here to hear about this topic, which is hard to find, or it's not covered in your average college meteorology instruction. So, but very interesting topic and important, especially to this region of the world where we depend, say, on HF radio and things that can really be influenced. Okay, so thank you all for joining, and I will get this out on YouTube in a day or two. All right, see you.
My pleasure.
Yep. See you for the next webinar in July.